there are times when we want to do something called traversal. And the name traversal and search is often used interchangeably, sometimes meaning the same thing, sometimes not. Up until now, we talked about binary search trees, and we knew what we were looking for, and we always knew where to go, left or right. But other times, we want to do some operations on the same node. As I mentioned before, we might want to add a color property to this node. Perhaps if we had a user node, we want to add an age property to all our users that are in a tree structure. Perhaps we want to add a shape property to these nodes. Or perhaps we don't have a sorted tree. It's not a binary search tree. Or we have a graph that has no order to it, in which case we have to visit every node. Or maybe we're working at Google and our boss asked us to, hey, can you check if our binary search tree we entered into our database is correct and that it's actually valid, and making sure that the left item is always lower than the right item? And in order for us to check that, we have to touch every single node. But how would we go about doing this? You can think of traversals as visiting every node. And as you can imagine, because we're visiting every node, that's an O of n operation, linear time. Up until now, we did loops to visit all of our other data structures, like arrays, linked lists, hash tables, queues, stacks. So how do we go about doing this in a data structure like a tree or even a graph? Well, luckily for us, there's two ways of doing this that we need to learn. One, it's right over here. Do we have to do a tree traversal? Or do we have to do a graph traversal? In that case, our two options are the exact same. We have breadth first search and depth first search. And sometimes this is called traversal instead of search. As you can see, both with trees and graphs, it's the same thing. The big O is O of n because we have to visit every single node using these two techniques. But let's review why this is important and why we don't store everything in just lists, which are simpler to understand. Well, the main benefit of why we don't put complex data into just lists, like arrays that are sorted, is that we get the O of log n searching. What about hash tables? Those are easy. Well, remember that hash tables aren't ordered. And at the end of the day, we represent data with different data structures based on their needs. And trees and graphs work really well for a lot of cases, which we've already discussed. When we search for things, we have the benefit, but also when we insert or delete items, we have better performance than something like an array. But we also maintain the order that we wouldn't have otherwise with hash tables. Trees and graphs are used a lot when we want to search nodes or visit every node, and it represents a lot of data that models the real world. Now, let's explore how these two traversal techniques work. I'll see you in the next one. Bye-bye.